Hey guys. All right, good. Thanks for coming, folks. Good to see everybody. Alrighty, welcome back. Lovely Tuesday here in Boston. I have not heard Marty Walsh do a press conference yet as part of his new role as Secretary of Labor. Labor? Yeah, he's Labor. I wonder if anyone will be able to understand Marty when down in Washington. Yeah, that's a bad one, huh? Leanna. All right. Today we're going to dip our toes into virtual memory, and we'll do it today and Thursday. Today's lecture is more of a kind of an overview kind of thing, and then on Thursday we'll dig into a couple of the details so you can see sort of behind the scenes how it's working. Just a heads up that I'm getting my first COVID vaccine on Wednesday afternoon. So depending on how I feel, I'm assuming I'll feel okay for Thursday's lecture. But if it goes south, I'm getting the Moderna, the first one. If it goes south on like Wednesday night into Thursday morning, I'll have to cancel class on Thursday. But I'll make that call probably really early Thursday morning. So keep an eye out on Piazza. If I don't show up on Thursday, that's why. Yeah, I'm pretty sure it's the Moderna one. Late July. Oh man, that's tough. Yeah, you get to go to Gillette and do it at the stadium. That'll be fun. Alrighty, speaking of Gillette in the stadium, did you guys see Jeopardy last night? So Aaron Rodgers is hosting Jeopardy for the next 2 weeks. Who knew, right? It was hilarious. So Aaron's okay. It's very low energy for some reason. Apparently he loves Jeopardy. He did get got, Dev, and that's what I was going to mention. So the final Jeopardy, the returning champion, there was no way he could win because one of the guys, it was a runaway. And so his answer to the final Jeopardy question was, who wanted to kick that field goal? Which was a huge dig on Aaron, because you might remember in January at the Super Bowl, it was Buccaneers and the Pack, and they were on the 8-yard line with the ball with like 3 minutes to go or 2.5 or something. And they were down 2 scores. They chose to kick a field goal instead of trying for the touchdown. And, and then Brady got the ball back and just never gave it back to Green Bay. So boy, did Aaron was a good sport. He saw it, he laughed, he like, it shook him, I think, for a moment, but then he laughed it off. So funny. Aaron wanted to go for it. It was the coach who wanted to kick the field goal. They should have gone for it. Is homework really 50% of our grade? Yeah, I think it is. It's like 25% is midterms and 25 final and 50% homeworks, I think. I believe that's the breakdown. How many more? How many more do you want? Please, sir, may I have some more? Ow. I believe 2 more. So PS5 will come out probably tomorrow, and it's going to expand on PS4. It's an interesting problem set. You're going to extend your calculator so that it reads and writes from a file. So you get to play with file IO, and you're going to do a conversion from infix to postfix notation. So the file will start out with infix notation, like 4+3. Those get converted to 4+3+. And then once it's converted, it's just like you hard coded that string and you give it to your RPN evaluate function. So it's really just the file IO and the conversion that we're looking at. You might need to make a couple more tweaks to your code, like your node probably needs another field, probably. But minor tweaks, I think. And then there'll be one more after that. So you'll have 7 altogether. Is there an alternate exam time? It's going to be, it'll be like the midterms. So it'll extend over a day or 2 for the final. Jonas. Yeah, so 2 more coming for you. And for the last 2, I'm going to try to focus the graders more on like just a couple of small parts so that they're not grading the entire thing, and maybe it'll speed it up a little bit. Haven't figured out grading in this course yet. Clearly grading's got an issue, like it's a serious issue. We have a lot of people, like we have a lot of graders. There's something about the grading process that isn't working. So we'll have to do a root cause analysis. What is that, Kaiban or something? You do the fishbone analysis to get to root causes. Yeah, actually, Jonas, that's it. That's it. There's just a lot of you. And this is a small course. There's only a couple hundred in this one. What do we have in this course? 220, 230, something like that. I mean, I feel bad for like Vahid and Dave Sullivan and those guys, like CS111, 112. Those are just massive courses. I think Vahid had 900 students this semester. That's wrong. What are we going to do to that, right? The department just keeps growing. All right. Actually, I'm running out of time already. Yeah, so 2 more problem sets coming. You really just have 2 problem sets and a final, and that's it. That's not bad. Another month to go. The finish line. Yeah, like don't prematurely celebrate there, Ian. Hey, I'm almost done. Yay. All right. Thanks for tying that all back, Ian. That was awesome. All right, let's talk virtual memory. So again, we're going to cover like concepts today, and then on Thursday, assuming there's a Thursday lecture, I'm sure there will be. I've read that the first vaccine is not an issue, and I'm old, so apparently it's younger people who are getting symptoms. So we'll talk concepts today, and then on Thursday we'll dig into the kernel structures a little more, so you can like see how it actually works. It's pretty close to this. It's just a couple of details we need to talk about. All right, so far we've been talking about the process, right? Remember that I should have put the picture here, that nice process picture, it's of memory. So I got 4 gig of space, a gig on the top is for the kernel, the other 3 gig are for the process. And from the process's standpoint, it sees just in a 32-bit system, like it just sees this really clean, contiguous chunk of 4 gigabytes of memory. Starts at 0, next one's 1, next one's 2, goes up from there. It's just a really clean space. The problem is that like there are a lot of processes. On this box, this is activity monitor. I've got almost 500 processes running on this machine. Every single one of those processes gets 4 gig of memory, of virtual memory, process space. Well, each of those gets I've got 500 of them, right? And it's 4 gig each. How many gig is that? That is 2,000 gig. That is 2 terabytes of memory that they're occupying. But how much memory do I actually have? I've got 8 gig, and that's it. That's 2 processes worth, and I got 500 processes. So the question is like, how do I manage the physical memory in such a way that all of these processes see 4 gig of space, and it's usable space. It's not like, oh, you can't use this part because there's not enough. Like, no, they all get a full, well, 3 gig because of the kernel space, but they all get the full 3 gig of memory to play with. Like, how does that work? That's what virtual memory is. So the answer is virtual memory. It allows us to essentially map the process's memory in such a way that it only occupies a small amount of physical memory, and that way I can share physical memory. So let's look at just like really basic, simple memory systems. This is non-virtual. This is like old school. You might see this in a controller, like if you were playing around with microcontrollers, building embedded systems, that sort of thing, like really small processors. They just address memory directly. So I've got some physical address lines. Looks like I only have 4 bits. I got some physical address lines coming out of the CPU, and those addresses, like each address is one of these cells of memory, and that's it. There's no abstraction, there's no indirection. It's just What address are you looking for? That's the memory cell. Read and write a byte. The address, by the way, kind of looks like this. So here I've got, this is a 4-bit memory space. So in 4 bits, I get 2 to the 4th memory locations, 16 memory locations. So you just basically break the address into 2 pieces. So if, like here, the address is 0100, just break it in half. The top half is the column, the bottom half is the row. And so if I arrange it like a grid like this, like here, this address, 0100, so that selects column 1. 01 is 1. So column 1 is, that's column 0. This is column 1. And then which row? The bottom half of the address is 00, so it's column 1, row 0. Column 0, column 1, row 0. That's that green dot right there. That's that address. There's 1 bit there. It's either a 1 or a 0 sitting in that intersection. The purple one is address 1110. Top half is 11, which is 3. So I'm selecting column 3, and then the bottom half is 10. That's 3. Sorry, 2. 1s and 2s. So it's a 2. So it's column 3, row 2. Column 3, row 0, 1, 2. That's that location. The little purple dot, there's a bit there, 1 or a 0. So that's how memory generally is arranged. Like regardless of how large it is or what kind it is, it's generally arranged in a grid like this. And we split the address high, low, and select a column and a row. And then at the intersection of that, depending on the kind of memory, there's going to be a set of transistors or an electron well or a capacitor or something to hold a 1 and a 0, a 1 or a 0. And then if I want to read it, like you just, break down this address, find the intersection. Is it a 1? That's a 1. If it's a 0, it's a 0. Those lines, by the way, we were playing around with these in A1. Let's see, find a nice one here. Picture of that. I don't need that anymore. Just trying to find the address lines. Maybe it's on the next slide. Yeah, I guess so. This is a Z80 CPU. So this is a really small, this is a 16-bit CPU. These came out in, so Z80s came out in 1978, 1979, that time frame. And you can see here the address and data lines. That's the entire CPU chip, by the way. You can see most of the pinout is occupied by memory. So the address bus is 16 bits wide. I'm going to break it into row and column. And then the data bus, I've got a byte toward the data, 0 through 7. If we looked at the actual, here's the board. This one. In fact, here's the chip. That's a Zilog licensed Z80. That's the chip itself. So these are the pins. So in this picture, I can't do it, can I? In this picture, like I've got A1, pin 30, pin 31, and so on. Actually, we're looking at the other side, right? So pin 27, which is this, this memory line, pin 27 on the top corner here is this pin up at the top corner here, and so on down the line. So how am I going to read memory? It's actually a pretty simple process. So if we're going to read physical memory out of the CPU, this actually takes several cycles, several ticks of the clock, machine cycles. So it places the address on its address lines, and then you got to wait for those to become stable. So what's happening there is annotate, draw. So I'm going to go from like a 0 to a 1 on each of those address lines, or maybe from a 1 to a 0. There's going to be a transition from one side to another, 1 or a 0. So if it looks like this, I'm going to have this transition. That's horrible. Undo all that. Here I'm at 1 level, like at a 0, and I'm going to transition to a 1. The shape sort of looks like this. So that signal is going to bounce a little bit. It's going to take time to do the transition itself. I mean, it's a short amount of time, and this is exaggerated, but it's going to take some time to go from one level to another. And then once it hits the new level, it's going to bounce a little bit. And so you literally have to wait for the signal to become stable, and then you can like latch it in. That time period is really, really, really short, but it exists. And so we have to wait for the signal to stabilize before we can do anything. So the signal stabilizes, I've got the address on the address lines, and then you assert the read signal. That the read lines over here. Let's undo this. Clear them, stop that. That's this read line, I believe. So here's the address. We just dropped the address on the address lines. And now we're going to assert the read line. That's pin 21. And then once that stabilizes, I'm going to strobe the data line. The data line basically is the signal to the memory that, hey, I'm going to do a read or a write. I've got the read signal lit up, so it's going to be a read in this case. Once I've strobed that line, and strobing just means you put a pulse on it, like a strobe light. Beep. So I strobe data, and the memory controller then is going to decode that address. It's going to break it down into column and row, and then place all the bits on the data line 0 through 7, and then it's going to raise data ACK. Data ACK just means that the data is ready. The signals have stabilized, they're ready to read. Then the CPU can go and read them, and it's going to turn off its lines at that point. So all of that takes 3 or 4 machine cycles. I think it's 4 cycles on a Z80. It's probably around the same on the current Intel chips too. But it takes time, right? That's a significant amount of time. And by the way, it's just these things. So I've got 8 data lines here, but data is organized like this, right, in memory. So I've got row and column, and when I decode a row and column, I essentially get 1 bit. So each of these is just 1 bit sitting in memory at 2 different addresses. If I need a full 8 bits of data, like a byte of data, I've got to have 8 chips. That's why when we see pictures of machines, they look like this. They look like this. So here's the CPU up here, and then down here is the memory. There is, what memory chips are these? Those are CAM41.6s. These might be 1K chips. I think they're 1K chips. So I've got, I think that's it. Do I have 4K memory in this? I might have more than 4K. Anyway, here are the memory chips over here. And you can see I've got 1, 2, 3, 4, 5, 6, 7, 8. Oh, there's 9. 1, 2, 3, 4, 5, 6, 7, 8. Oh, there's a 9th one. So I've got essentially 1 chip per bit across the data line. So that's maybe D0, D1, D2, D3, D4, D5, D6, D7. And then there are 4 banks of them. Basically, they're just contiguous. They lie next to each other in the memory space, the physical memory space. That last bit, by the way, so I've got 9 chips here, right? There's 8 of these. I only have, I've got 9 chips. I got 8 data bits. Like, why do I need the 9th one? Anyone know? No computer engineering guys in here? So the 9th bit is a parity bit, P-A-R-I-T-Y. Parity is just a way of doing error checking, a real simple error check across 8 bits. I can set a parity bit and then check that parity bit. It'll give me an indication if there was a single bit error in that memory. It doesn't work for even numbers of errors, just odd numbers. And that's it. Great. So it's actually a pretty simple system. Here's another one. So here's the machine. Same idea, right? It's actually a pretty similar layout. I've got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Looks like I had extra parity bits here. 1, 2. Yeah, I've got, like, here's a bank of 8. Here's a bank of 8, and I've got at least 1 parity bit for each, maybe 2. Why do I have so many? 8, 9. Huh. It looks to me like there's an extra memory chip in there. I don't know why. But like, this is an interesting problem. So here I've got, this is a 16-bit memory space, but look at my data line. Oh, it's really hard to see. there are only 8 data lines. I'm sorry, 8 address lines. So it's a 60-bit memory space. Addresses go from 0 up to 2 to the 16th minus 1. And I've only got 8 address lines. What's happening here is that this particular machine, this might even be, this would be a 68,000 maybe. I'm trying to think of what CPU this might be. It takes an extra machine cycle. So it reads data in 2 parts. It only has 8 bits. It only has 8 address lines. And so it puts the bottom half of the address on the address lines, strobes those into the memory controller, and then it has to put the upper 8 bits of the address on the address lines and strobe the controller, and then let the controller know it's got the complete address. So it takes a couple of cycles just to get the address over to the controller, because I just don't have that many lines. And then that's why, the reason is because if we look at that Z80, that's the Zyology Z80, like there's just not that many pins, right? Like here's a new, it's an i7. There's an i7. That's an old i7. That's probably 3 or 4 years old. But look at all these little gold dots. Those are all pins on the back. These things sit into a socket that sort of has little springs on it like this. Each of these is a pin. There's hundreds of them, hundreds. On something like a Z80, yeah, I've got how many pins? 2, 4, 8, 6, 8, 10, 12, 14, 16, 18. I've got 40 pins. That's it. And I got a bunch of stuff to put on those pins. So there's just not enough room. So that's why those chips had to do 2 machine cycles to send out a memory address. They just didn't have enough pins. And now, of course, like, we've gotten better about manufacturing, and we can push more and more and more onto an actual single CPU. They've just got a lot more bins now, so I don't have to worry about that so much. So that's reading and writing physical memory in a flat space. There's no abstraction here. I'm literally just putting an address on some address lines, doing a row column breakdown of it, and then reading a bit, 1 bit in each, one for each location in the byte, and putting those on the data lines. End of story. Not a lot else happening there. The problem that we're dealing with, though, is one of the problems is it just takes a really long time to get out to memory. Like, memory's pretty fast. We're talking about RAM, essentially. RAM is fast, but it's still like an order of magnitude slower than the CPU. The CPU is just really, really, really fast. Going out to memory takes a really long time. If I have to go out to disk, like, that is 4 or 5 orders of magnitude slower than going to memory. And going to memory is at least an order of magnitude slower than reading something right out of the CPU. So it's this really interesting problem of timing, and it's why we have so many caches in computing. Like, usually what we're trying to do is slow, and we're trying to speed things up by keeping a local copy. For example, we had tons of pictures in A1. Here's an i7, this might be an i7. Was it a Nehalem i7? I think it was. This is an Intel CPU die. So this is, if you took this guy, you took this and popped this silver lid off of it, this is what you would see inside. That's the silicon chip. And this one looks like the 4-core machine, a 4-core CPU. So the cores are, here's a core here, here's a core, here's a core, here's a core, and here's a core over here. So 4 cores in the CPU. The registers, by the way, these are the registers in here. So these these plots of land, those little square plots of land, those are registers. And then on this CPU chip is cache. This is cache memory sitting down here on the bottom. These 4 groups, these large fields, those are locations for cache memory. There's 1 set of cache for each CPU. And my guess is, it almost looks like there's 2 layers of cache here. Like, it looks like these are the registers up here, it looks like this is local cache for that core, but then there's more cache out here. I'd have to look at the Nehalem architecture to see what those actually are. This should have video on it. Video is either going to be this chunk in here, this long chunk, or that's probably memory controllers down here. I think this is the video portion in the center here. They'll have video chips sitting on them. Why is it here? Like, why is, like, that's a lot of real estate, right? I mean, I could have fit 4 more cores on this thing. Like, why did I take up that real estate by putting memory on the CPU chip? It turns out that it's really, really fast there. So we're running into a physics problem. The physics problem is that light and electricity travel at the same speed. So electricity traveling through a vacuum is going to be doing 300,000 meters per second. Well, there's meters and there's seconds. And so if you know how far something is away from something, you know how much time it's going to take for light or electricity to get from one spot to the other. On a motherboard like this, that's a really long distance between the CPU and the memory down here. Like, I don't think we understood back then, like, this physical limitation of the speed of light. I guess we must have, and they probably laid it out like this because it was easier to put the expansion slots on this I/O bus right next to the chip. But like, this memory is really far away. It's going to take a non-zero amount of time to get an electrical signal from the CPU all the way down to this memory stuff down here. If we instead can put that memory right on the CPU chip, like here, like these caches down here, I literally can't get any closer to the CPU than what these things are. That's going to be the fastest memory on the box. We're going to use that for instruction caches. They're small. These are really, really tiny. Like, there's not much. These might be 1K or 4K memory, just really, really small amounts of memory. But it's worth taking up all this real estate on the chip just for the speed enhancement. And these days, kernels and CPUs are just really, really good about caching. So you're going to get hit rates in the cache. A hit is when you find something in cache rather than having to go all the way out to memory to find it. Cache hit rates are in the high 90% range for most modern CPUs. So most of the time when you look for something, it's sitting in cache already. You don't have to go out to memory. So that's why we just choose tons and tons of caches everywhere. We'll talk a little bit about cache strategies in a lecture coming up. And of course, that's, CPU cache is the fastest. The next stuff out, that's going to be fairly quick. But, if I have to go to disk, like, that's just an eternity. We try to avoid disk at all costs. So back to the original problem, which is that I just don't have a lot of physical memory. I've only got 8 gig in this box, and every process gets 4 gig. Like, how am I going to manage that? We're going to use something called virtual memory addressing, and it's a layer of abstraction. It's a little bit of complication, but it really, really simplifies the way we use memory within the process. It allows the process to see a fully contiguous 4 gig space that doesn't actually exist. Like, it's just sort of an illusion to the process. And it's this virtual memory system that makes all that happen. So here was if I go back a few, this is addressing physical memory directly. Just put an address on and then read the data. The complication we're going to add for virtual memory just goes in between those two things. So the CPU is going to address a virtual address. That virtual address is coming out of the process. And then we're going to translate that into a physical address. And it could be anywhere. Like, this address 4100, like, where does that live? I don't know. It's just somewhere in memory. It just lives somewhere in memory. Excuse me. It's going to be a little table that the kernel keeps that says, oh, you wanted virtual address 4100. It looks it up in the table and says, oh, that lives in main memory over here at location 4. So it's a translation table, essentially. We're going to treat this like a cache. So I'm talking about caching. It's a little bit like a hash table, Jonas. Maybe we'll get into that on Thursday. To be honest, I don't know what the Intel CPUs are using with, like a Unix kernel. I'm guessing it's some sort of hash. Although, no, I take that back. It's probably more direct than that. It's probably doing some tricks with math to do it. But we'll see. We'll see what it looks like. Can you tell I haven't read that part of the chapter yet? The bad part is, like, I used to work for a company called Digital Equipment Corporation, DEC, these guys. Digital Equipment Corp back in the day was Massachusetts' largest employer. We had 200,000 employees, almost 200,000 worldwide. It was 112 in the US, I think. But this was back when virtual memory was new. Like when I was working at Digital, I worked in a couple of groups. I worked in a course development group, and I wrote a lot of the systems courses for their VMS operating system. VMS stands for Virtual Memory System. And I believe, and I could be completely wrong because I worked there, I believe that we invented virtual memory for that operating system. Because prior to that, the PDP-11s, 70s, using POS and so on, were not virtual. And when virtual memory came out, like, it just blew everybody's minds. It was probably one of the most important advances in computing, at least in that decade, maybe in a lot of decades. Virtual memory is a really, really big deal. But yeah, exactly. And it was whoa, I can do that. And also it's so simplified the process view of memory that it made programming so much easier. Like, we didn't have to deal with reading and writing physical memory locations anymore, or worrying about what memory had been allocated. It's like, it just removes a lot of complication from the process side. From the kernel side, it adds a lot of complication, but it was a win, I think. Yeah, digital was fun. God, I remember my last role at Digital Equipment Corporation, DEC, was I worked in a research and development group. And one of my jobs was to travel around to all of the various business units that Digital had, and there were tons of them. And I had a presentation. I was trying to convince upper management that this new thing called the World Wide Web was important and that we should pay attention to it. And they didn't, and ended up folding. So if they'd only listened to me, they would still be around. That was must have been 94 going into 95. The web was just brand new, and the only site really I had to demonstrate was, it's so weird too. Like, this is like late 1994. The web was brand new, and one of the most popular sites was a coffee room at Cambridge University, the Trojan Coffee Room. Somebody had set up a camera pointing at the coffee pot, and they'd take a picture of the coffee pot every minute or so. So if you wanted to get coffee and you went to that school, you could pull up this page and see what the state of the coffee pot was. But that was like one of the only things we had to demo. That's why I wrote kidpub.com. Kidpub was a tool that I used to learn about the web, which was new, and so I had something to demonstrate. Like, I at least show them, oh, it's real simple. Here's how you build a website and so on. Anyway, that was good, the good old DEC days. It's crazy times. All right, so we're going to treat this as a cache. If you think of a program sitting on disk, the CPU can't do anything with things that are not in memory. So to run an instruction, to play around with data inside that program, anything that the CPU is touching has to be in physical memory before it can touch it. And so I've got this big program sitting out on disk. Disk is really, 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 really slow. If the CPU wanted to, like, access a memory location and it had to go to disk to get information about that location, it would just take an eternity. And so instead, what I'm going to do is take chunks of the program. We're going to call those chunks pages. it's a big chunk, like a, 4K or a K or something, bytes of memory. I'm going to take that information out of the disk file and move it into main memory, into physical memory. And now once it's in physical memory, now the CPU can access it. And to this point, we've been talking about things like the heap and the stack and so on. This is kind of separate from that. That's the view from inside the process. Now we're looking at the view from outside the process. It's just physical memory that's been allocated to the running program. And I've read that stuff, those bytes in from disk in a big chunk called a page, and then placed them into physical memory. Well, I mean, that's like, that's another problem, right? It's like, oh, great. So now I've got this situation where, do I have a picture of it? Maybe I don't. I mean, the situation, it's actually this. It's this. Here's what we're doing. This is the cache picture. So here's the virtual memory stuff out here. That's the program sitting on disk. When I need to access parts of the program, like to run an instruction or something, it has to be in physical memory. And so I'm going to read that page from the left and place it into physical memory on the right. So physical memory is shared by all of the running programs. We looked at Activity Monitor here. I had like 500 of them, right? They're all sharing physical memory, but it's at the page level. So here's my program over here. Oh, I need to access something in this part of the program's memory. Well, I'll go to the disk, grab that page, place the page in memory over here, and then write a little entry into a table to tell me where that memory lives in physical memory. So now when the process wants to do something with that memory, it's like, oh, I need to change this variable or run this instruction. This thing, going back a few slides, it says, oh, you want to change the variable that's addressed 4100. That's a virtual address. Where is it actually in physical memory? It's in this page over here, virtual page number 1. Where does virtual page 1 live in memory? I have a table that tells me, oh, it's down here at this location in physical memory. Cool, no? Well, now we have another problem. We talked about relative speeds. We have a slightly larger problem, which is, physical memory is really small, and I've got tons and tons of processes that want to use it. So I've got to deal with moving stuff in and out of that memory. There's just not a lot over here on the right. And I got lots and lots of these over on the left. They've all got to fit in. Like, how are we going to do that? So here's some terms that we're going to use. It's really just a cache. So we're going to use caching terms. If something is in cache, in other words, it's in physical memory, that's going to be called a cache hit. If I miss something, this should be like a miss/fault. I'm going to end up calling those faults. If something is not in physical memory and I've got to go to disk to get it, that's a cache miss. We're going to call that a page fault. Then I need to know, like, once stuff starts to fill up over here, I'm going to move these things back out to disk at some point, but I need to know if they've been changed or not. If something has been modified in memory, now I've got one version in memory and another version on the disk, and they're different from one another. I'm going to need to see, have I changed that page? And if I have, I'm going to have to write it back to disk at some point. So there's going to be some policies around when do I do write backs. And that's called cleaning up the cache or flushing the cache. Practically, I'm going to use that validation information when I'm moving something like this out, away, so somebody else can use that spot. If the page is clean, it hasn't been changed, I'm probably not going to write it back to disk immediately. The reasoning is that if this is an actively running program and I write this little purple page, this one, back to disk, well, if it's clean, if it hasn't changed, just keep it in main memory for a little longer. Maybe the kernel does have a little thing called a page pool. It's going to take that page and stick it into this little page pool just for a little while, just in case the program needs it again. And usually it does. And now it's in this page pool, which is in memory, the kernel's memory. I don't have to go to disk to get it. I just get it right from memory, which is faster. So that's the validation and write back stuff. And it's going to use tons and tons of tables to do this. We'll look at the page tables today. So page table, there's a page table for every single process, and it's this. That's the page table, basically. Here's the virtual address. Which page in physical memory does that live in? So page tables have, imagine it's living enough page table entries. So PTEs, each page table entry tells us for this page, where's it live in physical memory? And it's per process. So if I have 100 processes, the kernel's keeping track of 100 page tables. So page table looks like this. Here's my page table over here on the left. I'm going to address some memory, virtual memory. I'm going to hit this, this guy down here, the second purple one on the left. Well, where does that live in physical memory? I look in the page table. Oh, there's a valid bit that tells me it's in memory. Now I can read this entry. It's the address of that page. And then just go out to physical memory to work with it. And you can see they're just all over the place, right? They don't have to be contiguous in the page table. I just need to be able to find them in the page table. Actually, they're contiguous over here, I think. They don't have to be contiguous in main memory, in physical memory. How about let's look at a hit. So here's a page hit, a cache hit. I have a virtual address, look it up in the table. And if I've got a valid bit of 1, that's great. That's a cache hit. That means that that address is already resident in physical memory. I just go to it. Boom, I'm right over there. That's the simplest situation. What about a cache miss? So that'd be a page fault. A page fault is when I have an address and it's not in physical memory. I'm going to have to go get it from somewhere. It's going to have to be from disk, usually. So I've got the virtual address here. I translate it. Oh, the valid bit is 0. Shoot, I got to go to disk to get it. So here I get all the way down to here. There's my disk. And now I've got a, oh, shoot. Now I've got a real big problem, which is I just had a page fault. I've grabbed the page from disk, but where am I going to put it? Physical memory is full. At least this picture of physical memory is full. So now I've got to deal with, like, where is it going to go? This is a problem. What was I going to talk about? There was some little bit we looked at in, what was it? Oh, I was going to look at page faults. We did something I was like, something in A1. What was it? It was a page fault list. Bernard asks, what could be an example of a physical page? A physical page of memory is just a chunk of memory in physical memory. So if I've got I've got 8 gig of memory, each of these pages are going to be, it depends on the operating system. Typically a page size is 4K. So each of these pages over here, VP1, V2, and 7 and 4, all of these are 4K wide. So take however much memory, physical memory you've got, divide it up into 4K pages. That's how many pages I've got in memory. And what's in that page, it's your program. It's going to be executing code, like actual instructions. It's going to be data. Whatever the program needs, it has to be in physical memory to run. It's going to be in a page in physical memory, and that page is going to have an entry in the page table to show us where in physical memory that virtual address is. Like over here on the left, your code, like your running program, is going to be working with virtual addresses in its space. That's the picture of memory where we saw, the stack on the top, the heap on the bottom, the text portion, the read-only data portion, all that. That all looks like a nice, clean 4 gig space that starts at 0 and goes up to 4 gig. In reality, it's broken into pages. The virtual address looks nice and contiguous, but then each 4K chunk of that is going to have a page table entry pointing to its location in physical memory. And I guess the real thing to remember is that the whole program is not going to fit in memory all at once. It can't, because I've got so many processes needing memory. Remember, all the programs that are running share this memory, the physical memory, this stuff. Like, there's no way that I'm going to have an entire program in memory all at once at the same time. It's like, doesn't happen. Here's an example of, we're playing around with top. Oh, can I see it here? Yeah, here for example. This is top running on this Mac, and you can see, like, here's Zoom over here. Here's its page faults. We're up to, what are we up to? 1, 2, 3. 1, 2, 3. 300 million page faults plus, and it keeps going. So page faulting, it's not a big deal. Like, page faulting is an expected operation of the kernel. It's not that something's going wrong there. It's just efficiently using memory. All right, so that's a problem, right? Physical memory is full, and I just asked, I had looked up a page table entry, and it's not resident. I got to go to disk to get it. So I'm going to grab the page from disk. Where am I going to put it? I'm out of room. Well, we're going to drop into something called paging. So in paging, I'm essentially just going to remove a page. This is full over here. I'm just going to pull one out and then put the new guy in that spot. So I'm looking for, looks like VP virtual page 3. I got to pick one of these guys to yank out a physical memory, and then I'll put virtual page 3 in that location and then write a page table entry for it. That's paging. Now, this is called demand paging. So in demand paging, you wait until you need a reference to a memory location that's not in physical memory, and you have to go to disk to get it. So that's the paging operation. There are other ways to do it as well. If the page is dirty, in other words, it's been modified, it's probably going to be written back to disk. I don't really want two copies of that data that are different from one another, one in memory, one on disk. Like, that's a bad situation. And so if the dirty bit's set, like that page is dirty, and there's of course there's another table that keeps track of each page, and in the page header is an entry dirty or clean. Well, it's actually just a dirty bit, it's on or off. If it's dirty, it's been modified, I really need to flush it back to disk, because it's just not good having two different copies. If it's clean, I've not modified that page. So this guy here, if I'm going to take out, let's say I'm going to take out VP4. If VP4 is clean, really all I'm going to do is I'm going to move that page into a different spot. I'm going to pull it over into a kernel structure called a page pool, an unmodified page pool. That page is available to use again next time the program needs it. I'll realize, like, I'm trying to remember if that's a page table entry. I think it is. So the next time, like, this VP4 is going to get pulled out of physical memory. It's going to be placed over into kernel's memory. And I'll make a page table entry for it here saying, oh, by the way, that's over in the unpaged pool, the paged pool rather, and it'll just get it from there if it needs it again, instead of going all the way back out to disk. That's for a clean page. If it's a dirty page, we just write it back to disk. All right, so I'm gonna pull that one out, right? I'm gonna pull page 4 out and put page 3 in its place, it looks like. There's nothing fancy about it. I just go, it's like, oh, I need to page something in. Oh, physical memory is full. Which one am I gonna pull out? I'm probably gonna pull the page out that hasn't been accessed recently, assuming that I'm just not using it much anymore and I can afford to pull it out. Sergey says, wouldn't it make more sense to take VP1 out? It came first. Yeah, but VP1 might be main, and my instructions in main, I'm just running in a big loop. So I'm constantly hitting those instructions. Maybe VP4 has some code that was, a side branch of my code, or it's a piece of data that I'm not using right now. So I can afford to take that out. So I'm going to take out VP4 and just put VP3 in its place. And all I do really is just, literally just put it in its place and rewrite the page table entry. There's nothing fancy about that. Now that's paging. So as the process is running, as it requests memory allocation, it's going to be paging constantly. That's what's happening with Zoom over here. we're up to 310,000. Is that 1,000 or million? So bad with numbers. Million. It just keeps paging, right? This is just constantly asking for pages that aren't in physical memory, and they're being loaded in. If that doesn't work, like if physical memory is really, really constrained and I have a lot of processes running, physical memory is going to fill up pretty quickly. And it's going to be tough to find a page that is eligible to be taken out. Like they might all be active. In that case, I'm going to take the entire process out. So instead of just bits of its memory, I'm going to take the whole process and write the process to disk. That's called swapping. So swapping is at the process level. Paging, this stuff is at the, I guess they're both processes, but here I'm working with individual pages inside the process. Swapping, I'm dealing with the entire process. And it's going to go into a special file called the swap file. And at some point, as the system runs, it's going to start freeing up some memory, and I can swap that back in. Probably the next time it wants to run, I can swap it back in. So things that I would write to the swap file. It's not necessarily a bad thing to have a process written to the swap file. Let's say the process is running and it does a disk read. Disk reads are like really, 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 and I'm talking 4 or 5 or 6 orders of magnitude slower than the CPU. It's just really slow to get something from disk. Like, should we have that process resident in memory while it's waiting? No, like that's just a waste of resources. And so when I do that disk read, the process blocks because it has to wait. It's going to get pulled out of the CPU and probably get swapped out if it's going to wait for a long time. There's just no point in having it in memory. And then at some point, the disk read will come back and will wake up that process. It'll come out of swap and back in, and now it's active again. If I have a program that runs, only periodically, like we were looking at what was cron the other day, or in A1. It's there. And screw that one up. Thank you. If we do cron tab, here's cron. So cron is just a process that runs periodically. It just wakes up every minute or so and then checks its list of things to run. But again, like a minute is an eternity. So there's no reason whatsoever to have the cron process resident in memory. Just push it out to the swap file. And when it wants to run, we'll pull it in from swap. So putting something into the swap file, it's not necessarily a bad thing. It's kind of normal operation. However, if I'm examining a running system and I see it starting to swap a lot, that could mean that I have memory constraints that I need to be concerned about. I might need to add extra memory to it. And then it gets really bad. So, I mean, swapping can kind of go both ways. Like some things I'm absolutely going to swap just because they're sleeping all the time. Active processes that are swapping, that's a big problem. And if it gets really bad, we get into a thrashing situation. Thrashing is when I've swapped something out because there's no room, and then I try to bring a new program in and there's no room. So it gets swapped out and a new one gets swapped in, but there's no room for it. So it gets swapped out and a new one gets swapped in. It just swaps and swaps and swaps. And the system ends up doing all of its time swapping. That's called thrashing. And when you get to a thrashing situation, you just need to shut the box down and probably throw some more memory into it if you can't distribute those processes somewhere else. That's a serious memory problem. You can actually hear it if you've got a physical hard drive on your machine and you're in a thrashing situation. If you put your ear down next to it, you'll hear it go as the read-write heads ratcheting across the platters, doing all the swapping all the time. So that's a bad situation. When else do we play with these things, like these page tables and so on? Every time a process gets pulled into the CPU. So physical memory is shared by all of these processes. All the programs running share physical memory. And there's only one, well, I mean, you know, we saw this one had 4 cores, right? But generally speaking, you really can only do one thing in a CPU, one instruction stream, generalized. So I can only do one thing. I can basically run one process at a time in a CPU, end of story. Well, like that, I've got 500 processes that want to run on this machine, and this is a small machine. So there's got to be some way to like fairly allocate CPU resources. And what's going to happen is I'm going to let a process run for a short period of time. It's called its quantum. And then once that time is up, that whole process gets pulled out of the CPU, and a new process gets loaded up into the CPU and starts running instructions. And that could happen, you know, let's say it's a millisecond. The quantum is a millisecond. So every millisecond, 1,000 times a second, a process is getting pulled out of the CPU, a new one's getting loaded, and now it's starting to execute. Well, anytime that happens during that, it's called a context switch. When I do a context switch, all the stuff associated with that process, all of its registers have to be reloaded. So that means when I do a switch, I got to save all of the registers, all of them. I've got to save the page tables. I've got to save, there's dozens of tables. All of those have to get saved before I can bring the new process in. And when the new process does come in, it's got to load up all those things. All the CPU registers have to be loaded with the values they had when that process was context switched out. So there's this massive movement of data on every single context switch. And it's very expensive to do. Like, and it's not even work. Like, this is all just overhead. It's all accounting. There's no real work being done. Sorry, accountant majors. There's no work being done there. It's just moving bits around so that I can run another program. So context switching is a big deal, and it needs to be as efficient as possible. Like, one way we can fix that, I guess, is that, so for example, if a process is running and it makes a virtual memory request and it's a cache miss, so it's a page fault, that means I've got to go to disk to get that page. If I'm going to disk, that process is going to get pulled out of the CPU because it's going to have to wait for that disk read to finish. I'm not going to wait for it. I'm just going to pull it out. It's called blocking. I'm going to block that process, pull it out of the CPU, pull somebody else in. That's an expensive thing. And it would have been nice if that process could have just keep running until its end of quantum. I can avoid the disk read by reading more stuff into physical memory. And that's this notion of locality of reference. Locality of reference says that when the program's running, it tends to stay in the same spot roughly. So if I've got a 4K page, you know, as my executing instructions are all going to be kind of within that 4K page, like pretty close to one another. And maybe as the program is running, it's going to kind of move down, and maybe if instructions go into the next page, and now I'm going to spend some time in that next page. But it's not that I'm doing lots of just random reads and writes all over the place. Most of the work is done in a small group of addresses that are all kind of around each other. Well, we can use that to our advantage so that when we go out to do a page read, for example, from disk, so I hit a page fault, oh shoot, I got to go and load that page. I'll load that page, let's say it's page 2. I'll also load page 1 and 3. So now I've got pages 1, 2, and 3, or maybe I'll do, if it was page 2, I'll do 2, 3, and 4. That means that I've got more pages in memory. And so as my program is running, it's running, all spending time up on page 2, and now it's sort of drifting down. Oh, now I'm into page 3. I've already got page 3 in memory. So there's no page fault there. It's just another virtual hit in physical memory. That locality of reference ends up creating what we call a working set. And the working set is just the set of pages that the process is currently using resident in physical memory. That working set tends to stay pretty constant for most programs. I mean, some programs, have different profiles, but most normal programs are going to be in their working set for a while. And in fact, I just remember this. It's so weird stuff that comes back to you. I haven't thought about this since the 90s. So when the process spins up, when I'm actually just starting a process, I'm going to set its working setup to begin with, because I have to do there's going to be a page read for sure, because that first instruction when a process gets loaded in and it's a brand new process to run, the first instruction is going to generate a page fault. So I got to go out and grab those. Well, to avoid that, as I'm loading the process up, I'll load the first several pages of that process into memory, and now they're ready. So that first instruction, it's already in memory. I don't have to do another page fault, which would be back to disk. And that working set size is adjusted. I don't think I can configure that. I'm thinking of Linux. Can I adjust the working set size in Linux without recompiling the kernel? I think I've got to change something in a header and then compile the kernel again to have the updated working set size. In VMS, we could adjust it on the fly, as I recall. Like it was a per process thing. What's the working set for this process? And I could grab a bunch of pages or fewer. I think Linux is all for one. Anyway, that's locality of reference. It makes a lot of sense. And so usually what we do is combine that with this notion of demand paging. So the initial page load will be several pages that the process probably needs to start. And then we'll do demand paging from there so that as it needs additional pages, we'll go grab them from disk as necessary and use locality of reference to grab a couple of pages around it to grow the working set. What we really, ideally, we would keep growing the working set until it hits some maximum value, and that's all the memory we would need. And practically speaking, in most modern systems, there's enough memory that we can do that now. Back in the old days, we couldn't. So you should be able to get your entire working set into memory at some point. As you do more and more demand paging, your memory allocation will grow. All right, fun stuff, huh? I love talking about this stuff. All right, so bottom line, these are just like, this is high level stuff. Like we'll dig in a little bit on Thursday, assuming I'm not ill, knock wood, knock veneer. So bottom line, you can think of virtual memory as sort of a cache for disk, but what we're caching really is a program and its data portions. And the reason we need it is because of multitasking. So as I'm moving processes in and out of the CPU, they're all sharing this limited physical memory resource. I have to have some way to fairly allocate that physical memory. And we do it with pages. The page size is adjustable, but as I just said, I think it's a compile time kernel feature for most of the kernels. Oh, I even say it. That's fine. So weird. So weird. I actually wrote this at some point and then I forgot that I wrote it. Getting old sucks, man. But all of this works through tables. So it's the kernel keeping tables. It's just keeping track of which virtual page is in which physical page, whether the pages have been modified or not, when was the last access time, and so on. It keeps statistics on all those pages and it uses those statistics to make decisions about when to pull a page out, when to replace it, and so on. And all of this really is just so that our processes can see this really nice, clean, contiguous, from the process view, it's just a big empty hall like this, with the seats or memory locations, just all in a neat line, all numbered sequentially. And the reality is much messier than that, but the kernel hides all of that reality from the process. The process sees this perfect, beautiful 4 gig of space and can do whatever it wants to with it. All right. That's it for today. So Thursday, we'll dig in further into the kernel structures that make all this happen and some of the algorithms that it's using. And that'll be memory week. And then next week, we'll do something else. All right, guys, that's it. I'll let you know probably late tomorrow night, rather, Wednesday night, about Thursday's lecture. Assuming I can stand up. I'll be fine. I'll be fine. See you all guys later. Thanks, guys. Appreciate you showing up. Happy vaccination. Nice. Thank you, Bernard.